a lot. I think first of all, I would like to say to everyone that I hope every one of you guys and your families are safe and well at home. Hopefully you are coping in the best possible way under these difficult circumstances that we're having to deal with. And well, I also hope that in the next few weeks, hopefully we'll have the opportunity to share some interactions and to continue our research and our work together. Well, second, I would like to thank Frank for the invitation. This is an amazing opportunity to share with you guys some of the experiences that we have. And I hope the information that I'm going to share with you, it's going to be interesting, maybe useful even for you guys in the next few weeks, months. Maybe you can start some project that we can work together also. So, well, this afternoon I'm going to share with you the presentation entitled From Residues to Nanocomposites, where we will be speaking about some different alternatives to remove from contaminants from wastewater. This presentation was prepared by my student, my PhD student, Cristina Meira. She's working at DPN, and I'm also working at DPN at the Department of Materials. During my presentation, we will be discussing some concepts about contaminants in polluted water and some of the technologies, some of the basic, conventional, and some of the non-conventional technologies for contaminant removal. We will zero in emerging contaminants, which are a particular class of contaminants, which are being more important in the last few decades. And of course, we will present some results related to the contaminant removal using biofilters, two types of biofilters particularly, and constructed wetlands. And towards the end of the presentation, I will be dealing with some ideas about the use of nanoparticles and industrial residues to remove emerging contaminants. Of course, at the end, I will give you some conclusions, some basic ideas of our future work, and hopefully that will be interesting for every one of you guys. So, as everyone knows, water is essential for life, first of all, and it's the most important natural resource that we have available in our world. It's not only necessary for life, but it is also required for a variety of industrial activities. So whenever we have it, let's say that nobody is that interested, but if you don't have it, then you have economic and social problems. Actually, water scarcity is likely to be a big problem in the next few decades, because up to 2/3 of the world population could have problems because of water scarcity. So it is interesting to work about the possibility of removing contaminants and using clean water for a variety of purposes. So whenever you use water, whenever you wash your hands, you wash your clothes, you will be contaminating water. If you live in a city, this contaminated water will go through a set of pipes. It will go to the sewage network, and then next to a city, probably you will find a wastewater treatment plant. From this wastewater treatment plant, you will remove some of the contaminants that you have in water, and the clean water will go either to some water bodies, like a river, or maybe in some cases you will try to reuse water, for instance, for irrigation purposes, or even for flushing the toilet in some cases. And that is basically the cycle that we are trying to work with. What is wastewater? Well, basically, wastewater is any water that has been used by a human being, because whenever you use water, you add something to water which wasn't there, and that is a contaminant. And wastewater can come from industrial sources, like in the mining industry, for instance. You will find heavy metals, lead, chromium in the mining industry, for instance. Could come from agriculture, and could come also from domestic sources. Here in this presentation, we will be dealing basically with this type of wastewater, domestic wastewater, which is classified in gray water, black water, depending on the sources that you have. And we will also work with a particular set of contaminants, as I said. So, is a contaminant in polluted water? Basically, contaminant is any substance that affects the physical, chemical, biological properties of water. every time you want to use clean water, you want to use pure water. So if you have odor in your water, for instance, then maybe you have a problem with contamination. You can classify contaminants in many different ways. Here you have one way to classify these contaminants in physical, chemical, biological contaminants. Of course, in some cases, you can have, like you can see here in this slide, you can have one source of contamination. Here, the solid in the bottle will be a physical contaminant. If you have something inside the bottle, that could be a chemical contaminant. And if you have microorganisms growing next to the bottle, that will be a biological contaminant. Could be a pathogen that could be harmful, for instance, for human beings and so on. So these contaminants in polluted water can be classified in many different ways, as I said. One of the most common contaminants are related to organic matter. These organic matter include feces, food waste, debris. Uh, they come usually from domestic wastewater and also from agro-industry, from farms, from your house, of course. And these are some of the contaminants that we will be dealing with in this presentation. We will also work with some other contaminants, which are the emerging contaminants I'm going to discuss in a few minutes. Of course, you have also some physical agents, such as suspended solids. If you have pieces of plastics, for instance, that is a contaminant in water that you want to remove. So if you have these contaminants, you want to use pure water, then you would like to be able to remove the contaminants that you have in this water. That is extremely important. This has been even classified as the objective number 6 development goals. And whenever you have that problem, contamination, you will have to decide what type of wastewater treatment technology you will use to remove these contaminants. For that purpose, you will have to know what is the volume of water that you want to deal with, what are the costs that you can consider in your technology treatment, and of course, you will have to consider what type of contaminants you have. You can have many contaminants in wastewater. You can have macro contaminants, micro contaminants, as you can see here. And there is a problem on the source also of this wastewater that we may like to treat. So if you want to see if your treatment technology is effective, you will like to measure a given set of parameters. For instance, if you want to deal with organic matter, maybe you want to monitor the chemical oxygen demand. In some cases, if you want to deal with solids, you will try to see what happens with the total suspended solids that you have in your water. If you have emerging contaminants, you will deal with the concentration of pesticides, for instance, in the water. With heavy metals, you will see the concentration of ions of nickel, lead, and different metals, as you can see here in this slide. So these technologies have been developed around the world during the last 600 years, perhaps. And just during the last 100 years, we have developed some modern ways to treat wastewater. You can classify these technologies in some preliminary treatment, primary, secondary, and some advanced technologies. In these cases, in the primary, for instance, treatment, you will try to remove sedimentable solids. And in secondary technologies, you will remove also some suspended solids that you can have. So the preliminary treatment, you will sieve things that are in water. You will use breeze traps, flotation systems. You just want to remove big contaminants, big pieces of materials that you have in water. In secondary treatment, you just don't do that. You use physical, chemical, biological processes to remove different types of contaminants. You take away the large solids, and then you try to remove the smaller contaminants, the molecules, the pathogens that you have in water. For that purpose, you can use conventional technologies, activated sludge systems, coagulation, flocculation. That is going to be very useful in some cases. But you can also use non-conventional technologies. One example is a constructed wetland. Well, for all of you guys that don't know what is a wetland, basically that is an ecosystem which is covered by water. that could be permanently or seasonally, every season. And it has, as you can see here, some plants, has soil. And what you do is you take some contaminated water. This contaminated water goes through the wetland, goes down, goes also in some cases horizontally this way. And as the water goes down, you eliminate the contaminants. How do you do that? Well, in some cases, there is just a physical effect because here you can have soil that will that will block some of the contaminants that you have in water. Here you will also have some bacteria, some microorganisms that are growing in this soil, and that will help you to remove some of the pathogens, for instance, that you have in your contaminated water. And you can have some other microorganisms that will be growing also next to the plants, for instance. So there are a variety of mechanisms that can be used here to remove the contaminants that you have in a given amount of water. If you are next to a big city or in a small town, then you can use conventional technologies that can be decentralized systems or centralized systems. You use decentralized systems when you have something like more than 10,000 inhabitants, for instance. You can adapt those technologies to smaller populations, and you can also use this type of systems when you have small towns around, like the ones that you have here in Ecuador, for instance, in many places, in many provinces of the country. Whenever you use these technologies, however, you have to consider the cost and the knowledge that you have to have at the moment of installation, operation, and maintenance. In some cases, these type of technologies are going to be very expensive, and that is, of course, a problem, always. You can use, as I said, also non-conventional technologies. These non-conventional technologies could include these constructed wetlands. These are called constructed because these are artificial wetlands. You make them on purpose to be able to remove contaminants from water. So in this case, you take a substrate material, and this substrate should be good enough to let you grow some plants here, and you will spray some water on this bed made of this substrate. Water will flow horizontally, vertically, or both, and then here you will take the clean water outside of the constructed wetland, and then you will remove the contaminants. As everything in the material world, as everything that you can imagine that it's made by a human being, materials will play a very important role in these technologies. These materials that are used here for substrate will let you grow and develop plants and microorganisms, which is extremely useful. These materials will also help you to absorb, to remove some contaminants by absorption or adsorption with D, and will also help you to retain some nutrients because the microorganisms that you have here and the plants will take some of the nutrients that you have in contaminated water, and that will be good. That will be nice because at the same time that you have plants growing, you will remove some contaminants. And these materials are very important, not only in these non-conventional technologies, but also in the more advanced technologies, such as the one that you can see here in the hybrid system. Here you also can have a material which is going to help you to remove some contaminants. This could be activated carbon, for instance. It will let you grow some microorganisms. It will help you with absorption of some contaminants. And again, it will let you work with organic matter and nutrients to remove them as contaminants. You can also have filtration technologies as the ones that you can see here that will help you to remove from micro to nano elements. You will remove bacteria, virus, macromolecules, and that will help you clean the water. So these conventional and non-conventional technologies can be very useful. In our case, in our work, we focused on non-conventional technologies. Some of them are these wetlands that I was talking about a few minutes ago, and the other type of technologies that we use are biofilters. In these biofilters, you have the same configuration as in the wetland, basically. Here you have a substrate, but you spray water, water goes down, then you take here clean water. In this substrate, you will have a variety of microorganisms that will help you to remove the contaminants and to eliminate some toxic substances that you can have in water. In some other cases, you can add other organisms to your biofilter. You can put some worms. A worm basically will eat some of the contaminants that you have, and it will work like in a small wastewater treatment plant, because it will take out the contamination and then it will use those contaminants for growing. And also you can have plants. These plants can grow in a given substrate. They will take also some of the nutrients and that could be toxic in wastewater, and they will use these substances to grow, which is going to be nice. What is one of the problems? Well, one of the problems that you have here in this type of technologies is that whenever you want to use them, you need large areas because they take a lot of space. So it's not very convenient for a city like Quito, but may be very convenient for a relatively small town or medium-sized town. What is one of the problems that you have? That you have to have this substrate material, and this is going to be relatively expensive. In some cases, this can represent something like 50% of the investment that you have to make to put this technology to work. So here is one of the areas of our research. Besides having these common contaminants, organic matter, nutrients, you can also have some more modern contaminants, which are called emerging contaminants. These contaminants have become relatively important during the last few decades because we started to see these contaminants in water just during the last few years, 20 years, 15 years, in Ecuador during the last decade even. And these contaminants come from substances that in some cases are not regulated. In some other cases, these substances are pesticides that we use for agriculture. They are personal care products and steroids, hormones, household chemicals. So you have a lot of products that are nowadays used by almost everyone. And these have some of these emerging contaminants on them. What is the problem? The problem is that these emerging contaminants are persistent. They last very long periods. In some cases, they can also be bioaccumulable. You can have bioaccumulation and biomagnification with these emerging contaminants. So that is a big problem, even though they appear in very low concentrations. So you want to remove those emerging contaminants. What is one of the problems? Well, the conventional wastewater treatment plants that we have in our cities, they are not very efficient to remove these emerging contaminants. And well, you can use some advanced technologies, but the problem with these advanced technologies is that they are relatively expensive and they could be very costly. They could cost something like $35 to $85 per inhabitant per year. So it is relatively expensive. If you want to do something like that for in a small town or a big city, even it's going to be even worse. So what happens in Ecuador and Latin America? Where in Ecuador, the advantage is that you have a lot of water, but one of the problems is that you don't treat water. In Latin America, just something like 22% of the wastewater that we have is treated, and the other 80% will go to the water bodies, will be used for irrigation purposes without being treated, and that will give you the possibility to happen diseases, for instance, and that is the real problem. In Ecuador, it's a little bit better than the average, but we just treat something like 35%. So we need to improve that. So we require some research, hopefully, and development on different ways of using this type of technologies. Here in Ecuador, you can have conventional treatments, as the one that you can see here in this slide, in many different places, different systems, depending on the size of the city, of the amount of money that you have. And you can also find just a few, but you can find them, some of these non-conventional technologies. As I said, in these non-conventional technologies, one of the problems is that you have to invest for buying the support material, which is the one that you will have here in this vermifilter. The vermifilter is the one that you have with worms. But the advantage is that these non-conventional technologies are cheaper than advanced technologies. It could cost something like $26 per year per inhabitant. So it is going to be very interesting if you are able to use these technologies in some cases. So far in my presentation, well, I have tried to give you an idea that wastewater treatment it's a must, is an obligation, particularly in developing countries, such as in Ecuador. Traditional wastewater treatment plants, they are not very efficient to remove emerging contaminants, so you want to do something with them. And non-conventional technologies represent a good alternative because they have lower costs, lower technology requirements during installation, during operation. You don't need such a big team for maintenance and things like that. And within these non-conventional technologies, you can use biofilters, you can use wetlands. Of course, in these cases, materials are of paramount importance because you will have to deal with materials to remove contaminants in many different ways. In our group, we are trying to work particularly with non-conventional technologies, and our focus is to use for support materials agro-industrial residues. Since in Ecuador you have a lot of these materials available, you have a great agricultural industry, and of course you have the byproducts. And if you don't use them, maybe if you use them, maybe you can have an opportunity to valorize those materials, and it's going to be also very helpful. We also try to use some more advanced materials such as nanoparticle, nanostructured materials to combine them with these agro-industrial residues, make some composites, and that is going to be useful to remove the conventional contaminants, the more common contaminants, organic matter and nutrients, and also the emerging contaminants. That is the idea. That is our focus. So in the next few slides, I will present some of the results that we have obtained during the last few months. And those are related first with using biofilters to remove organic matter and also to remove nutrients from contaminated wastewater. What is the idea in this case? Well, in one of the studies that we performed, we used wood chips and peanut shells as support material for biofilters. In the biofilter, what you can do is you can set a column like this one, and then you can have here different layers of materials. We use an active layer. This is the one that has the agro-industrial residues that we are dealing with. And then we can use some other materials in the middle and support layer. In these cases, in this area, in this active layer, you can use many different things. First of all, you use the agro-industrial residues. And whenever you use these residues, the idea is that you will have some microorganisms growing because they will help you to remove some contaminants. But you can use not only the support material, you can use some earthworms, you can use some plants, and you can use a combination of plants and earthworms in hybrid systems. So in our case, the idea is to put some synthetic domestic wastewater here, the water will go down, and here you will get clean water. That's how a biofilter works, basically, for our study purposes. What did we want to study? Well, we wanted to know if we can use peanut shells in our biofilters. We also wanted to know if we can work feeding water continuously or intermittently, because you, in a house, for instance, you don't always have water going down the toilet continuously. You will do that just a few times a day, a few times a week. So it's not like that you are feeding water continuously. So we wanted to know what happens if you do it intermittently. And we also wanted to know what will happen if you use a certain type of plants on earthworms. That was the idea. So regarding peanut shells, well, peanut shells are a byproduct of peanuts. That is an industry that is relatively interesting here in Ecuador. You have a large amount of tons, something like 14,000 tons per year produced just in the coastal region. And you can have a relatively good amount of these byproducts of these peanut shells. That are the ones that you can see here. For instance, you will eat the peanut, you will get the peanut shell as a byproduct. These peanut shells are interesting because they have nutrient content which is relatively high that could help you for microbial growth. They also have good contents of lignin and cellulose, so they can be useful for absorption. So those were good candidates, but we didn't know that these peanut shells were used before to remove some contaminants. So that was the idea of the study. We collected the peanut shells, we washed, dried, and grind the peanut shells, and then we sieve the peanut shells to be able to get some relatively small particles to be able to put them in the biofilter, less than 2 millimeters. And then we first we try to define the amount of peanut shells that we can use to be able to grow these worms, which are the Eisenia fetida, which are very common worms. They are the same ones that you use for composting, for instance. And one type of plant, Heliocaris palustris, which is relatively common here in Ecuador, next to some water sources. And we first of all, we try to conduct some acute toxicity tests and some chronic toxicity tests because you don't know if the peanut shells are going to be toxic for these worms and plants. Well, at the end, we found that you can use something like 25% volume of peanut shells combined with some other material, in our case, wood chips, in a given biofilter. If you use too much peanut shells, you have mortality in the Eisenia fetida, and you don't have good growth in the plants. So that is the problem. So we took our 25% and we set up a system that looks like that. We tried 4 different types of biofilters. The first one was a common biofilter. In this one, you have our materials, our industrial residues, peanut shells, and wood chips. And here you will develop some microorganisms. That is the M here in the name. In this second biofilter, you will have the same material, but it will also use worms. So you have here the E of earthworms. You will use also plants. So here you have the P of plants, and you have hybrid systems in which you will combine worms and plants. You will take some synthetic domestic wastewater. This synthetic domestic wastewater was used for reproducing, to be able to reproduce our results. And this wastewater was also proved before in some different studies. So we are kind of sure that this works well. This water goes down, and here you collect the clean water. That was the idea. You will feed the water at different rates as the ones as you can see here. So it's not that you continuously feed water, but you have a given rate here. And you will measure different parameters to see if the contaminant removal that you are performing is efficient. Basically, we will measure the amount of solids that you will be able to remove in these filters, and also the COD, the chemical oxygen demand that you can have here. This chemical oxygen demand basically gives you an idea of the amount of organic matter that you have. So we characterized the lignocellulosic materials. We characterized what will happen with the worms and with the plants. We wanted to know if these worms will be growing in our system. We wanted to know if the plants were growing, which is going to be good, because if the plants, if they don't grow, that means that the biofilter is not going to be very effective during several months or years. And for the purpose of working with our wastewater treatment, we measured, as I said, the COD and the volatile solids. We also wanted to know what happened with the hydraulic conductivity and the head loss in the system, because if you have here the system and you put too much water or you put too much contaminants, you can clog the system. The system can be clogged, and then you won't be able to continue the treatment. So that's why we wanted to know what happened with the conductivity. And on the other hand, if water goes here too fast, you won't be able to remove the contaminants. That was the idea. So I'm not going to give you in this presentation all the details of the work, but of course, if some of you guys are interested, maybe I can discuss that particularly. I'm going to give you the more general results. First, regarding the removal efficiency, we were able to see that in every one of our systems, we were able to remove something like 80% of the contaminants related to organic matter. In this case, for instance, using the worms, we achieved something like 85% with this hydraulic rate, which was the smaller one. So we were able to say that the biofilters work relatively well. This is a relatively good efficiency for this type of system. On the other hand, studying the hydraulic behavior, we were able to see that this hydraulic rate, 0.5 cubic meters per day per square meter, was the best hydraulic rate for removing organic matter. This was the smaller one, and that was the hydraulic rate that helped us to have the water going through the biofilter during a time that was long enough to be able to remove the contaminants that we have. And also, we were able to see that these worms and plants improved clogging. We avoided clogging using these plants, and also solid removal. What happened here was also that the worms continue growing. Here you can see what happened with the worms before and after the treatment, the plants. And here you will see the total weight of the worm. So the worms were growing, which is good because they will continue helping you to remove contaminants, and the plants also will continue growing. So whenever you have the peanut shells just in the 25% of volume will help you to improve the environmental and operational conditions of these biofilters that will be we were trying to study. A second study that we performed was related to the use of constructed wetland. In particular, these constructed wetlands are very popular, let's say, around the world. I was in Australia last year, and I saw that you can have these constructed wetlands even in the parks, in the city parks. But here in Ecuador, for instance, they are not very popular, even though they will be very useful. And we have something like 200,000 constructed wetlands around the world, but here in Ecuador, we just have a few, as we saw. So what was the idea? The idea was that if we can use a plant like the one that you have here, which is a native plant in the Amazon basin in Ecuador, maybe we can take the advantage of having these plants for removing contaminants in the wetland. And we can also do something else. Since this is an ornamental plant, if you have an ornamental plant, then you can grow these plants, and then you can sell them. And actually in Ecuador, we export this type of plants. So that will be another advantage of using these wetlands. So we took this plant, we conditioned the plant, we adapted the plant, we took some measurements of the plant because we wanted to know if the plants will be growing in our constructed wetland. And we set up a system that looks like this. We have a system in series. Here we have a system in which contaminated water, the one that you have here, was flowing vertically. And this was connected in series with the constructed wetland in which water was flowing horizontally. Here you have the contaminated water. Here you have the clean water. You measure what happens at the inlet and at the outlet, in this case. Here you have a support media, which is just gravel with a given size. And the interesting portion was the use of the plants, as I said, in this couple of cases. In this wetland, you will have water staying during 3 days to be able to remove the contaminants. And this in the second wetland, you will have water during 4 days. So you will have a cycle, water comes here, stay here, and then it will go out without the contaminants. Well, that is what we hope. We wanted to know what will happen with the plants, so we took the measurements of the plants. We wanted to know what happened with the microorganisms being developed in the system, and we also wanted to know what happened with the removal efficiency. For that purpose, we measured the COD, the volatile solids, and the ammonia, nitrates, and phosphates in our case. So again, I will give you some of the more general results only. In our case, we were able to see that the removal efficiency was relatively high also. In our case, was something like 86.7% for removing organic matter. And regarding nutrients, we removed almost 96% of ammonium, and nitrates were also removed. Phosphates were also removed in this system. The second good thing was that this Heliconia stricta Huber provided adequate conditions for the growth of microorganisms that were the ones that were helping to remove contaminants in this system. So these are systems that are useful for removing organic matter and nutrients. But as I said, we also have some other contaminants, such as the emerging contaminants, and we wanted to know what would happen if we want to remove these contaminants from water. For that purpose, we started to work only with batch processes. These batch processes are the first step in the laboratory scale study, and we started to work with caffeine and triclosan, which are relatively common emerging contaminants. Well, caffeine, as you can imagine, is present everywhere. You can find caffeine, of course, in coffee, in a variety of food products, in medicine, and in many different products. And triclosan, irgasan, it's found in basically in personal hygiene products, disinfectants, detergents, relatively common, and they have been detected in Ecuador and also in South America and Latin America in many different places. So what was the idea again? The idea was to use some agroindustrial residues to be able to remove these contaminants, first of all, from synthetic wastewater. And for that purpose, we considered that, well, these agricultural residues have almost zero cost or no cost at all. You just have to take them. In some cases, they will give you these residues for free. In some other cases, you will have to pay a relatively small amount of money to get these residues and to be able to use them. And you have the possibility of using them for adsorption purposes and for removing contaminants. In our case, we were dealing with peanut shells again, and we also studied what happened with rice husk and banana peel, orange peel. Well, banana, it was very interesting because here in Ecuador you have a large banana industry, as you can imagine, as you know. And the idea was to see if these residues will be useful for contaminant removal, because we know that they have high efficiencies for removal, not particularly caffeine or triclosan, but some other contaminants like heavy metals in some cases, or oils, as you can see here. And that was relatively new. We didn't find some studies, for instance, in which you will see peanut shells being used for removing emerging contaminants. So what do? Basically, you take the residues, you wash them, you dry them, you grind them, you screen them, and you work with different particle sizes, because we also wanted to know what happened with the particle size that we have for these contaminants. Here you can see these particle sizes basically as the ones that you will use in our systems. Again, we tried to characterize these residues. We measured the amount of lignin, of cellulose, of extractives that you have in the systems, and we calculated the system efficiency for removing caffeine and triclosan, and for that we used UV spectrophotometry just to be able to see the amount of the concentration that you had before and after the removal, the amount of contaminants that you have before and after the removal. We set it up as a process. Here you have our batch processes being set up. We tried different concentrations, going from 1 milligrams per liter to 50 milligrams per liter for calibration of the process, and then we used just a concentration of 30 milligrams per liter for the case of caffeine, for instance. And then we we put the adsorbent, which is the agroindustrial residue, and the contaminant is removed, is adsorbed to the residue. So we measured that, and we got some of the results that you can see here. Well, these curves will give you an idea of what happens whenever you have, in this case, caffeine, in this case, triclosan, and this gives you the amount of, well, the percentage of the emerging contaminant removal. As you can see here, in all of these cases, you can remove basically 100%, 90% of these contaminants. But in the case of caffeine, for instance, in this plot, you can see that that will happen after 3 hours, 180 minutes. You are able to remove something like 85, 90% of the caffeine present in a synthetic wastewater. In this case of triclosan, if you wait something like 60 minutes, you will remove 90 to 95%, more or less, with a given dosage of these adsorbents. When you use rice husk, well, if you use small particles, we had a problem because we just reached 70% removal, and then the removal efficiency started to decrease, depending on the dosage that we used. Well, that was explained because we think that the material is agglomerated, and that agglomeration doesn't help you to remove the contaminants. In this other case, in this plot, you can see that you can reach almost 100% of removal with a relatively large dose, but you use also large particles. So we were able to remove most of the contaminants that we have in the case of caffeine. In the case of triclosan, whenever you use this type of adsorbent, this rice husk, you can reach almost 100% of removal after 60 minutes, as you can see here. In this case, you can see that you can remove basically 100% just using a small amount, 1.5 grams per liter of rice husk, which is a relatively low dosage. So what happens? Well, as you can see here, the agroindustrial residues work well, but you don't reach 100% removal in some cases, and in some cases it takes too long. So the idea was to be able to combine nanoparticles, these residues, and we did that. We were thinking about what kind of nanoparticles will be nice to try. So we were thinking about all the particles. Then we decided to use magnetite, which is an iron oxide. We prepared some nanoparticles using the co-precipitation method. We obtained nanoparticles, which are something like 30 to 50 to 60, in some cases, nanometers. Not that small, but relatively good. And we combined the nanoparticles, which with orange and with banana peels in our composites. You can see here what happens with the removal efficiency, with the absorption that you have in the systems. Here you have this plot. It's just related to the orange peel. The red one is related to the banana peel. So these materials, these residues, are extremely good for removing these contaminants. But whenever we use them, we have to use relatively large doses, such as 3.5 or 9.5 grams per liter in these two cases. If you use magnetite, the good thing is that you can reduce the doses. The system becomes more efficient. So in the case of orange peel, you can remove almost the same amount, but instead of using 3.5 grams per liter, you just need to use 2.5 grams per liter. That was the advantage. So reaching almost the end of the presentation, what I can say is that well, agricultural residues can be very efficient for removing organic matter and nutrients from contaminated wastewater. Also, as I said, some ornamental, some native plants that you can find here in Latin America, or in Ecuador particularly in our case, can be used in constructed wetlands to remove the same contaminants, the organic matter and nutrients. And when you think about emerging contaminants. These agricultural residues can also help you to remove these contaminants from synthetic waters. And this removal can be more efficient if you combine these agricultural residues with nanoparticles, which is the idea. Of course, these results are relatively interesting, but we still have a lot of things to do in the next few months and maybe years. One of the things that we want to do is that we want to try simulating real water instead of using just synthetic wastewater. And we also want to use this synthetic wastewater and real water, which is enriched with emerging contaminants, which is something closer to reality, closer to the reality that we find here in places like Ecuador, Latin America, and around the world. Another thing that we want to study is the possibility of going from these batch processes in the case of emerging contaminant removal to these filtration, continuous filtration technologies, because if you use batch processes, you are not going to be able to remove contaminants in reality. If you set up a column like the one that you can see here, you can take synthetic water or real water, and then you can clean the water that goes through this column. So that is something that we want to study in the near future. We want to escalate the process from batch to continuous filtration. That is one of the ideas in the next future. We have been dealing with wetlands and also with biofilters, but we also want to see if we can combine different non-conventional technologies and some advanced technologies in some particular cases. Another possibility that we still are thinking about is the modeling of the process, because if we model the process, maybe we can have enough information to be able to design better treatment systems, and that is something that we want to do in the near future. So for that, we have to consider a lot of problems. Of course, whenever you use nanoparticles, maybe some of you guys are thinking about what happened with the toxicity of nanoparticles, because if you have a nanoparticle in this system, you don't want the clean water having some nanoparticles at the end. So that is a problem. You also have to deal with that. And you also have to think about what happens when you combine organic matter with emerging contaminants, because there will be some problems about detecting the contaminants, looking at them properly. But that is what happens in reality. So that is something that we also want to study. So these are some of the ideas that we are thinking about for the near future. And well, hopefully that has been interesting for you guys. At the end, I would like to acknowledge some of our collaborators. In this case, Cristina Villamar in Universidad de Santiago de Chile, María Belén Aldaz at Escuela Politécnica Nacional, a group of our students, which are the ones that do the hard work. And of course, this project, these works, these results would be impossible without the funding from different organizations, Escuela Politécnica Nacional, Universidad de Santiago de Chile, y Fondesit. And well, thank you.
Thank you so much, Victor. Excellent work. You already have some questions on the chat, starting from Federico Sinche, and then going down the list. I don't know if you can see the chat.
Yeah, I am just going through the chat. Well, first of all, thank you guys for the questions. I think I will start with the one from Federico. Well, Federico is asking about the bioaccessibility of the contaminants in the wastewater treatments and the fraction of the contaminants that remain after remediation. Well, actually, in our systems nowadays, we have just a small fraction of the contaminants. As I said, in most of our cases, we are able to remove something like 90%, 85% of the substances, but take into account that we are using synthetic wastewater. So that will give you a relatively small amount of contaminants present in the wastewater, which is going to be something like 20%. And in some cases, you will have to use for that system in series with a second system to be able to remove that 20%. That depends also on the standards that you have, of course, because whenever you have this contamination, you won't be able to have zero contaminants at the end, but you want to remove 99 in some cases, in some other cases, 99.9%. So you will have to use systems in series in some of our cases. Well, I hope that gives an idea of what Federico was asking. Antonio Diaz, thanks for your question, Antonio. He is asking about the possibility of scaling up and the cost associated with the process in order to be competitive. Well, in this case, I can say that that is one of the main motivations for our studies, because these systems are relatively cheap. And another thing is that these systems can also be operated by someone that doesn't have knowledge or engineering knowledge, for instance. So you don't need knowledge about technology or maintenance to be able to operate the systems. In some cases, the systems can be operated by a community, and they are relatively low cost. What is low cost? In some cases, something like $25 per person per year in a relatively small place, in a relatively small town. What is in a small town? Something like less than 2,000 inhabitants for a decentralized system. Frank is asking about data for removing sulfur or fluorinated compounds in our systems. Well, actually, we don't have this data now. We were focusing first on organic matter and then on emerging contaminants. In some cases, you can find some data from previous studies from some different authors for removing this type of materials, but we have also some information about some regarding heavy metals in our cases, using our lignocellulosic materials, our industrial residues. I will be very happy to share with you guys this information in the next few days or weeks. Well, Paul is asking, nice question. Well, he said that there are some technologies that are used to remove contaminants, and also they can recover energy from these processes. Of course, this is something that is extremely nice. We would like to do something like that, because these systems also have, well, you have a system, biofiltration system at WETLAND, for instance, and the mechanism for removal, it is also related to the mechanism of adsorption, and that is the mechanism that is related to the movement of charges. So you can use the systems to recover some energy. I have seen some of the systems and some studies of those type of systems around the world and in the country. We have not done something like that in our case, but we are preparing a study using just that type of technology. We will try to measure what is the amount of energy that we can collect if you have one of these non-conventional technologies for removing contaminants. And that could be used, as Paul says, in a building, for instance, that could be used in a community to obtain a relatively amount of energy, but maybe something that is enough to power some small devices. Well, Frank is asking the possibility of having iron oxide nanoparticles dissolving and contaminating water. Yes, of course, that is one of the problems. We are still trying to solve that problem and to investigate a little bit more about the toxicity of these particles that could affect what will happen in a real system. But that is still a challenge. Definitely, whenever we think about this type of processes, we have to study what will happen with not only with the batch process, but also with the column. And to remove some of these particles, we are also thinking about some possibilities of recycling the particles. So at the end, maybe we can try to use these filtration systems also to take out the particles that are going down with the water that we are trying to clean. We need still more data, and we need to set up an experimental system, of course. Well, Efe Lopez says, if I know about the Navy's composition of the rice husk, because I understand that it's rich in silica. Of course. In that case, the question is about the mechanism that you can use for removing the contaminants, I understand. Yes, that is true. In fact, we are thinking about using rice husk to obtain silica and well, nanoparticles of silica, and using these nanoparticles of silica to absorb some of the contaminants. And in that case, yes, the absorption mainly is the main responsible for the removal of the contaminants that we can have here. As I said, I don't have the complete answer, but I'm thinking that some of your questions are basically some ideas that we can think about in the near future for us to improve our work. The last question that I have, it comes from David. He's asking about the stability of the nanoparticles. Well, these nanoparticles, they have a problem actually. These nanoparticles, they can be easily oxidized, and they go from magnetite to hematite relatively quickly. I don't think that that is completely a bad thing, because hematite and magnetite, they have low toxicity. So these are relatively interesting results for that purpose. But we are still thinking about using not only magnetite but some other iron oxides. And we would like to see if hematite, for instance, it's better to remove some contaminants, and maybe if they are not that toxic as some other particles that you can use in some of these systems.
Well, thank you so much, Victor. You had a lot of questions, and you know, I hope we can continue and develop collaborations with APNA when everything gets get back to normal. We do have a lot of people working on water treatment, water purification, removal of pollutants. So I think there are a lot of opportunities. Thank you so much again, Victor, and I hope we can meet in person when everything gets back to normal. And thank you to share your work today, and also I think your student was participating to the presentation, right, today?
Yes, she should be here, I suppose.
Yeah. Okay. Excellent. Glad that everybody was able to connect. Thank you everybody to connect, students and professors, and hope to see you soon, Victor. You have a good day.
Thanks a lot, Frank. Well, I hope the results presented were interesting for every one of you guys. I hope I can answer some of your questions in the next few days if you feel that my answers here were not good enough. And thanks a lot. Maybe in the near future, as Frank said, we will be able to share, and maybe we can work together in the next few projects during the next years. Thanks a lot.
Excellent. Thank you so much, Victor. Bye-bye.
Bye-bye.